Well, I have to say I'm honored and quite a bit in disbelief that I'm standing here and talking to a sitting head of state. That is certainly a first for me, so thank you very much again for inviting us to this. Let me just switch the presentation here over. Okay. Part 3, we started with sustainability at the urban level, continued with sustainability at the building level, and now let's drill down just a little bit more for 20 minutes or so and look at the systems level. And when I say systems, what I mean is building systems. There's the building envelope, there's the lighting system, the electrical system, the mechanical system, the plumbing system, fundamentally. And let's start with the thermal envelope, the building envelope, which is the facade, also the roof, but also elements below ground. Everything that separates the building from the outside, where we have the uncontrolled climate, to the inside, where we try to maintain a controlled, comfortable environment. And when we talk about thermal efficiency, what we're talking about is our desire to limit the transfer of heat. So these are two very simple diagrams that illustrate a building. On the left side, you see a building that you would like to remain cool, and on the outside it is warm. And just in terms of fundamental physics, the warmth will never stop trying to get into the building. It's like, imagine the building was underwater. The water would never try to get into the building. You have to constantly pump it out, so you have to constantly work on keeping a building cool. Otherwise, if you do nothing, there will eventually be an equilibrium, and the building will have the same temperature on the inside than it is on the outside. And the reverse logic applies in the winter, in cold climates, when you heat the building, you have to constantly work on keeping the cold temperature out. So most people don't think a lot about that, but there are different ways of how heat transfer happens. There are three fundamental ways: conduction, convection, radiation. Conduction is, very simply put, if you have a hot piece of metal, you put it in the fire, the other end is going to get hot pretty soon too. Think about a pot on your stove. That's conduction. Molecules don't move, but they touch each other and transfer heat energy. Convection is the moving of air or of a liquid. So if you have a fan that moves air, that's convection. And then radiation is heat energy that travels through space, through a vacuum, like from a fire, from the sun, 150 million kilometers away, I believe, and it's still pretty hot here on Earth. Travels through space, doesn't need a medium. And all of these mechanisms happen with respect to the building envelope. There's convection through a window, there's conduction through a massive wall, there's radiation through a window, and we have to deal with all of them. And the window is typically sort of the weakest spot in the envelope. That's where we lose or gain the most of the heat. And with modern windows, we have double insulated glass, and we have a whole range of smart layers in there at our disposal, but it still remains the weak link, and we want to limit heat transfer through it. So that's our job as building envelope consultants. Then there are various analysis tools that we can use, but the ultimate goal is still always the same. There is the goal of minimizing heat transfer through the building envelope, and we have certain scientific values that we use to analyze that. There is R value, R like resistance. There is a U value, which is only the inverse of the R value, and there are certain ways to calculate it and to model it, and there are some fundamental principles that we would like to adhere to in order to make it as efficient as possible. And why do we care so much? We care so much because we, at least in the United States, certainly much more so than here, we have sophisticated energy consuming mechanical systems that either cool or heat a building, and well, if the building envelope is no good, is literally inefficient, well, it goes out of the window, and you have to work so much harder. The systems have to work so much harder. We have to spend so much more energy just to keep a comfortable interior environment. So what we advocate is your money is better spent not on supersizing the systems, but on creating a super insulated building envelope where you keep the heat or the cold in your building. And that's what we're advocating for. There are many ways to do that. And one important aspect to keep in mind is it's not only about the R value of, let's say, a typical piece of wall construction, like a brick wall or a curtain wall, but there's a thing called thermal bridging when you have a penetration of a highly conductive material, like metal. Metal is always very conductive. You lose a lot of heat at this one location only. Imagine you have a bucket full of water and you drill a little hole. The integrity of the remainder of the bucket doesn't matter. You're going to lose all your water through the hole. And the same logic applies to a building envelope. You would like to avoid punctual or even linear penetrations. Here's an example of a great building. We did it, the New York Times building, which has, you see there in the corner, exterior load-bearing columns. At every floor, there's a whole range of beams that penetrate from the outside to the inside. That's a thermal bridge. That's where you're losing heat. And that's where you always, depending on the climate, create problems sometimes with condensation. If the air is too humid and then it's too cold, there will be condensation. The other one is a stunning piece of architecture in Chicago by Studio Gang. And you see those undulating balcony slabs? Well, they are all linear thermal bridges at every level of the building. Certainly very inefficient in terms of the building envelope, but I have to admit it's still a stunning piece of architecture. So maybe sometimes those traits are legitimate or allowable, you know, from a green perspective. I want to show you one quick example here. It's a soccer stadium in the United Arab Emirates we recently worked on, where we analyzed with this software here, how can we shade the exterior with exterior shading elements. Those were like fiberglass panels that we put outside and in front of the building envelope there in order to minimize the thermal heat gain, which in a desert climate you certainly want to do. And you see in the graph on the lower right-hand side there that the blue curve is the thermal heat gain over the course of the year without those exterior shading elements, and then the really quite significant reduction that could be achieved with the introduction of exterior shading. I'll skip this one here. And let's move into the realm of energy efficiency apart from the building envelope. Well, you always have to relate the building envelope to the energy required on the inside of the building for the systems. There is a very intricate interdependency between those two systems. When we talk about efficiency and conservation with regards to the systems, we're talking about what I talked about earlier, all the mundane, almost, building systems, plumbing, heating, air conditioning, lighting, talking about boilers, chillers, all the stuff you keep out of sight in the basement or on the roof. There are many ways to buy high efficiency equipment, and maybe even more importantly, to have the control set up in a way that you don't cool a building if nobody is in there, let's say at night, that you automatically switch off the lights if nobody's in there. There's an immense amount of energy being wasted when interior spaces are conditioned or lit and there are no occupants. Look at the skyline of New York at night. There are many buildings fully lit up, and you know that not many people are in there working. So tremendous opportunities there. We can model all of that. We can bring in specific pieces of technology, so to speak, and in the interest of brevity, I can't run through all of them, but there is underfloor air distribution. There's geothermal heat exchange using the constant temperature of the ground below us to reject heat from the building. There are smarter pumps, there are smarter motors, there are more energy efficient lights, motion sensors. If you put the right strategy together, you can create a much more overall efficient building than the standard building, the average building. And we can model all of that before we build the building. We can tell the owner, if you do all of this, you may be able to save X% of energy, X% of money that it would translate to. Here's an example from an office tower in China where we did the energy modeling, as we call it. We model the energy over the course of the year for the summer, for the winter, for the different uses, and we can predict the savings. And the chart on the right side shows the according to different energy efficiency measures, how we bring down from the baseline, as we call it on the left side, by measure after measure after measure, how we achieved a predicted 25% energy reduction there by high efficiency systems. A quick word about the power infrastructure for our building. This could be pertinent to big single buildings like skyscrapers in New York City. We have a couple of buildings where we have those systems here, or to whole districts, to whole neighborhoods. I'm talking about combined heat and power systems, meaning that you generate your power, your electricity in your own building or in your own neighborhood by either fired by gas or some other fuel. And the great advantage of that is, if you look at this chart, is typically the power plant generated power, a stunning 63% of the energy is lost, either transmission losses or even more so heat, waste heat, which just goes up the chimney, literally. So if you have a smaller power plant, mini power plant in your basement, you can capture that heat and use it either for heating your building or for providing the hot water, domestic hot water for the bathrooms and the kitchens. Incredibly smart thing to do. Here's a diagram of how a combined heat and power plant looks like. We don't have to spend any time on it. Another very intriguing concept is ice storage. Very, very simple technology, really, if you think about it. And it takes advantage of the fact that, at least in the United States, and I would assume a similar dynamic is at play here, is that the price for electricity goes down at night when you have a lower consumption, and goes up during the day when you have a peak demand for electricity during the day to run our buildings and for cooling. And what they do here, this is an example from a new building in New York, One Bryant Park, right at Bryant Park in Manhattan, where they have a series of very large containers of ice in the basement. They use the cheaper energy at night to freeze them, and over the course of the day, they let them melt slowly, and they cycle a cooling loop through those containers and cool the building, which means that translates to a load shift where you have a much more equalized loading pattern for your building, like on the right side of the chart, than you would otherwise have with the up and down pattern day and night. Very smart thing to do. There are ways to have on-site renewable energy on your roof, on your facade. The lower right hand is a building that we were involved with for a botanical garden in the state of Maine. This is a net zero energy building. It generates as much energy as it uses on site, on the site and on the building. We can model, as I showed earlier, we can model the solar exposure for photovoltaic arrays like we did here with this high school building. This is a modeling software that simulates here, I believe, the June 21st solar pattern for that building. We can, moving into the issues of daylighting and shading. As I said earlier, we all realize that humans respond positively to daylight, so we're trying to maximize the use of daylight and trying to minimize the use of artificial light by having the windows, maybe the skylights organized in a smart way, having technologies like light shells, other redirection devices, bring light deeper into the space. by having the right controls. Here's another study that we did to study the interior lighting environment of that particular hotel lobby in Libya, which is not being built now, as you may imagine, after the recent turbulence. I skipped that one here. Here's one maybe more to the point. That's a hospital for the veterans of the United States, and it has been proven with scientific studies a good lighting environment, daylighting environment, is good for the healing process. It's good for the convalescence process of the patients. So we modeled two typical patient rooms on the left, on the right, on the left and the right of this typical floor plan, and we can model simply the daylight factor in there and figure out to what extent do we have to bring in supportive artificial lighting. To what extent do we have to protect ourselves against too much light? There's like an ideal zone somewhere. If it's too much, you all know that if you sit in front of a computer screen and it's glaring, the sun is glaring into your face, you can't really effectively see what's on the screen. So there are many ways to do all of this. And moving from energy to water, I only will say that it's easy for us in the first world, so to speak, to forget that water is a scarce resource on a worldwide scale, and that as a matter of fact, every day people die because they don't have access to healthy potable water. This is a world map that shows the water stress, the relative levels of water stress throughout the world. And we have that stress in the United States, in the south. This is a photo of Lake Mead behind the Hoover Dam. Maybe some of you have been there. You see the former top level, and you see how much it has dropped. This is sort of a mineralic sort of bathtub ring there. It's at the lowest level ever, and they are already fighting about the water there in Utah, Colorado, Nevada, those states that draw from the Colorado River. So the response to that is really simple. Conservation efficiency. There are very water efficient new fixtures, toilets, urinals, lavatories, showers, all of that, and don't use more than you have to. Do you really have to have potable water to irrigate your lawn, your flowers? Maybe you can have a different type of flower that can live on the rainwater. So it's not rocket science. There is a way also to reduce, or rather to capture the rainwater, use it for green roof, like for example this one here. This is a building, the Transbay Center in San Francisco, for which we were the structural engineer. And also to capture and reuse gray water, meaning water that doesn't come from the toilet, but maybe only from the lavatory, that you could reuse for the dishwasher, or for irrigation, or for flushing the toilets. So there are, as illustrated in this diagram, multiple ways to reuse water, almost 2, 3, 4 steps down the road for various purposes. And I think I'm going to close with just one more little movie I'm going to show you, which I think shows you nicely how it all comes together. This is the same patient room that I showed you earlier here, which we were basically just as a little design exercise, we were studying what is the best geometrical arrangement of those exterior shading devices you see there in green. We call them the louvers. In order to, and we had a bifold objective, minimize thermal heat gain in the summer, maximize thermal heat gain in the winter. It's one of those climates where it's different with the seasons. And we have now powerful software that can run through, and we ran through, I hope it's starting, 600 louver geometries almost randomly. You see this happening here on the upper left-hand corner. On the lower side, you see visual representation of the thermal heat gain in the winter and in the summer. And after it has gone through that, there is a way to rank that. So this is something we couldn't do in the past with paper and pencil. We absolutely couldn't. So in a moment you will see how all 600 of them are being laid out. Should be any moment now. And then we can, well, let's wait for that. Reviewing the results. So now ranking the results for this particular criterion. And we could model this, we could do this kind of analysis for any type of criterion that you want to use. Maximizing X, minimizing Y. So here you see it all splayed out on a football field. And the green ones are the top performers. We rank them now. And then we can focus on the top 10. We can go back to the architect and say, which one do you like best? Which looks visually most attractive? Let's say, and we can hone in on those ones. Very powerful tools. And then as a third step, we say, okay, besides thermal heat gain, what does it mean on the interior of a building in terms of the daylight autonomy, the amount of time that we have to artificially light our room? And we can study that and then have another almost merged ranking at the end for analyzing different metrics. So very powerful software. I want to just close with a thought going back to this was sort of a pessimistic looking image I had in the beginning. You may remember we are living in the age of greenhouse gas emissions, and my hope is that we can move to the age of clear skies again, and that we as a building industry, we can be a big part of the solution to our global problems and challenges that we have. Thank you. Thank you.
Sorry about that. I just start off with a little location diagram. This is downtown Manhattan. You can see the red boxes there are the two main towers, World Trade Center 1 and 2, in the site. That's a photo, obviously, before September 11th, 2001, and you can see the various buildings there. And that morning, actually, we were in a conference room in my office, and we're having a meeting. It was pretty early, and in the middle of the meeting, one of our engineers kind of opened the door and he said, I don't know if you heard, but an airplane just hit the World Trade Center, one of the towers. So we happened to have a television in the conference room, and we're thinking, you know, it was probably a two-seater plane or something like that, a little, because years ago hit the Empire State Building, a little private plane, nothing happened. So we turn on the TV, and just as we turn on the TV, we see the North Tower that's kind of looking like, you know, all the smoke coming out, and then we see this other plane coming around. You know, it was all on television. And that one, and then you realize it wasn't an accident. It was big planes. And then the second one came around and hit the South Tower. And you could see that in the diagram on the left. And on the right is actually a picture of the North Tower looking south. But that's where the first plane went in, through the North Tower. And then the fireball that you see is actually the other plane hitting the tower number 2 in the back, and the fireball from the jet fuel and everything coming through. And you could see that in the actual fireball on the top, and then the bottom you see from another few minutes later. It's interesting because the North Tower was the first one to get hit, and the South Tower was something like 15 minutes after that, and yet the South Tower collapsed before the North Tower. And the reason for that, a couple of reasons. Well, one is that this is the North Tower, the north facade, that's where the plane went in. Now these buildings, if you remember the diagrams before, these were tube buildings. So all the lateral resistance in the building was in the exterior tube. So all those columns coming down, that's like an airplane fuselage. So that's all the lateral resistance. Now, what happened when the plane goes through, on the bottom and on the right, you can see the opening, but any of the loads from the gravity loads, from the dead and live loads, because those columns also take the gravity loads in addition to the wind loads, those loads were able to go around the opening, okay? It caused higher stresses those little red marks that you can see to the right and left of the opening cause higher stresses, but not enough to cause a failure. So their ductility, we talked about ductility before. You had some ductility in the steel, the load was able to go around. On the south tower, I don't have a diagram here of that, but the south tower was hit lower in the building, at a lower floor, and it went into the corner, the southeast corner of the building, which is a much more critical place, the building. So in the south tower, the corner was destroyed, so really the loads, it was difficult for them to go around that opening, around the corner, and also it was hit lower. So any stresses that were being exceeded, you had a heavier part of the building in the south tower because it got hit lower. So there was more weight, less capability to redistribute like this. And that's why that building came down. Now, why did our first reaction was that, well, okay, somebody's going to have to go and fix these buildings because they didn't come down right away, okay? As a matter of fact, we had a clear view to this. Our office was on 6th Avenue. It was before we moved to the building that Wolfgang showed. And we actually, outside my office, there was a roof setback, so some people were able to climb through the window looking out. I went out, and we were able to virtually see these towers, smoke coming out of the towers. So I went inside my office and tried to call the chief engineer of the Port Authority, who we knew. I mean, we didn't really do a lot of work with them, but, you know, at that time. But, you know, they're good friends of ours. So I tried to call them to see, you know, can we offer any assistance? And phone was ringing, and nobody picked up. I tried again, dialed again, then there was nothing. I didn't hear anything. And then I heard people right outside my window start screaming. And I was looking on the TV at the time, and that's when the South Tower came down, and people, they actually saw it fall with all the smoke billowing up. And, you know, the thought, and, you know, at least in my mind, and I've talked to a lot of structural engineers, it wasn't immediately obvious that these buildings were going to collapse because they didn't fall down right away. And the problem was the fire, okay? The fire, and it wasn't because of the jet fuel. Everybody, well, it was jet fuel and so many thousands of gallons, okay? The jet fuel burned off probably in about, you know, 30 seconds or a minute or a couple of minutes. The problem was the jet fuel spilled all over the floor, the whole floor plate, and started fires on the entire floor. Now, building sprinkler systems, and they had standpipes and everything in here, sprinkler systems are meant for office fires. You know, the fire starts in a garbage pail or something like that, and it's a localized type of thing. Here we had a situation where the entire floor went up in flames. And, you know, it went to the other floors above, and all of the sprinkler systems, standpipes, the whole fire protection system was destroyed when the planes went through. So there was no way to put the fires out. And that's what took the buildings down. The fires got hotter and hotter, and steel reaches a point where the strength decreases as the steel gets hotter. And it finally got to the point, now you have a situation where you have steel that's taking extra stress that it wasn't designed for, and now as time goes on it's getting weaker and weaker and weaker, and eventually that's why they came down, and that's why the second one came down before the first one. So this is actually a photo taken the next day, an aerial photo. On the left, those buildings, that's the World Financial Center buildings that were damaged, but were not destroyed. Actually, we designed a couple of those. The building up on top there with a big hole in it, that was World Trade Center number 6. That was the U.S. Customs building, and interestingly enough, the FBI had headquarters in that building. Lost a lot of documents and everything, and you can't really make it out, but I'll point. The World Trade Center number 1, the North Tower, was this one in here, and then the South Tower was down in this direction, and you had the Marriott Hotel here. So you had World Trade Center 1, 2, 3. That was the Marriott Hotel. World Trade Center number 4 was over here. World Trade Center number 5 was here. World Trade Center number 6 was here. And World Trade number 7 was across the street. So every building that had the World Trade Center name was destroyed. So this is just some facts and figures here. Obviously, a lot of deaths. 1 million square meters of space was destroyed. 3 million square meters was really useless. There were 2 million tons of debris, including 350,000 tons of steel. Now, I showed that picture, the aerial photo, and I just have to point out, when you went on the site, you couldn't, now these buildings were 110 stories, the 2 towers, and they were designed structural steel, steel framing, concrete floors, okay, metal deck, concrete. You couldn't find a piece of concrete on the whole site. It was all dust. It all just, when they came down, just everything was pulverized. So the another couple of things here which aren't in the slide that I wanted to point out. When the pieces came down from the top of the towers, they estimated that they struck the ground at 200 kilometers per hour from the top floor. And I show you, there's one picture here where some of the pieces went down about 30 meters into the ground, like a knife. There were over 100,000 truckloads of the debris that were carried to the landfill. There were about 40,000 workers that worked on the site, and there's fires that we saw when they came down. There were fires. There were 7 basements, okay, to the buildings. There were fires in there, and nobody could get to them because there was all debris all over the place. They burned for more than 3 months. So here's another picture of the buildings. All the buildings in gray were the World Trade Center buildings that came down. The ones in yellow were damaged around the site. And there's some had to just be cleaned, and others weren't affected. Yeah, so here's actually the names of the buildings, which I already mentioned. The other issue was the subways lines. We had 2 subway lines. You could see the white line, the solid, and the dashed lines. Those are 2 subway lines we had below ground that were within the area. Some of them were, well, they were damaged. I mean, when the buildings came down, they basically cut through the subways, so the subways were unusable. And that yellow line, that's a path, that loop in there, was the PATH train that goes to New Jersey. And that was below the ground surface, but coming through the basement of the World Trade Center. Now, the concern here was that we had not too far away, just to the left there, the Hudson River. And everything here was below grade in the basement. So the fear was that if there was water from the river that came into the site, and I'll talk about the slurry wall in a minute, we had these basement walls, and we were concerned that if the water somehow got into the basement, well, I'll show that next, that it would actually flood the subway and go to New Jersey and then come back into New York and flood the subway system. So there was a big concern about that. But there wasn't any obvious problem. There was no water coming in at that point. So this, I just have some site photos here, but you know, this is, oh, there's the river in the back, you can see. This is looking west. You can see the World Financial Center buildings. And this one here is the Winter Garden. So if you've been to New York and been to the Winter Garden, that's that. I'll talk a little bit about that later. But there's the Hudson River in the back. And the thing that struck me, though, is you would go there every day, and it was surreal. I mean, you'd think you were on a movie set, you know, some kind of, you know, disaster movie. And it was just, you know, just hard to believe that that had actually happened. You know, day after day you'd go there, you'd think you'd figure it out by then, but no, it just every day was like that. So what did the city do? New York City, the Department of Design and Construction, they immediately took charge. They called, in fact, it was on September 11th, they called us at around noon, and they said they had contacted 4 major contractors because they realized that the site was too big to call one contractor, and you know, there's just no way that one person could handle it. So they called 4 major construction management firms: Amick, Bovis Lendlease, Tully Construction, and Turner joint venture with Plaza Construction. They called us, and we went to the site that afternoon. And the way the project was broken up, it was actually broken up into quadrants. So we had in the upper left, we had the Turner, and they really took care of Building 7 and the other buildings around that area. And then the left, we had Amick, Bovis on the southwest, Tully on the east. So everybody kind of had their buildings that they were in charge of. So, you know, we had a number of challenges and things to do. And, you know, I've given a lot of talks about this, and people would ask a question and they would say, well, how, you know, did you have like some guidelines or something of what to do? And, you know, we didn't. I mean, you know, this never happened before, at least, you know, it was just totally unanticipated, you know. So what are you doing? We just kind of said, well, you know, we kind of made it up as we went along, you know, day by day. And then after a while, we got into the, you know, started formalizing certain things like documents and stuff. But, you know, we just kind of made it up as we went along. And a lot of those experiences that we have now have been taken. So there are now guidelines, national guidelines of how to, you know, address an emergency like this. But, you know, hopefully we don't have to use them. But, you know, but that was kind of a learning experience. So, you know, we had to do emergency damage assessment of the buildings in the surrounding area because you had, you know, a lot of buildings that had to collapse, and there were buildings with pieces of steel sticking in them. There were pieces that were knocked off buildings, and I'll show you some of those. So the idea was you didn't want anything else to fall down. That was the main objective. So on the September 12th and 13th, we had about 30 engineers from our office go around and look at buildings with the New York City Department of Buildings, the Fire Department, the Police Department. So that was done as an emergency type of thing. Had to identify unstable areas. Now, if you look at we had a basement there that's 7 stories deep, and there was debris piled. 110-story buildings. The 210-story buildings were little piles that were about maybe 10 stories tall. Okay, and then below that we had 7 stories of basement, and you had all this steel and pieces all over the place. And the way I describe it, I don't know how many of you remember there was a game called Pick-Up Sticks, okay, where you had little long sticks in a tube. You grab them, and then you hold them, and you let them go, and the sticks are all kind of all over the place. And the idea is each person that goes has to remove the stick without moving anything else, okay? And that's what it was like. This was like a giant game of pickup sticks. Buildings had to be demolished, shored, stabilized, so there were things that had to be done there. The next one was really the most challenging that we had. Identified locations where we could put cranes and all kinds of construction equipment, because the whole idea was to remove that stuff as soon as possible. I mean, it just psychologically, you know, you wanted to get that site cleaned up. Survey monitoring program, there were engineers from the city surveying, had lasers, levels and transits out, and making sure, you know, we wanted to see if there was anything moving that, you know, we had to address it. Inspect over 400 buildings in the area surrounding. The mayor, who was Mayor Giuliani at the time, said, I want, you know, and there were people in the surrounding areas that said, well, is my building in danger? I mean, this was felt as a earth tremor, 2.3 magnitude earth tremor at Columbia University, 34 kilometers away. Okay, so people were worried that there was some damage to the buildings and the buildings were going to fall down. So this was actually done, and I'll mention it in a few minutes. While we were on the site, the Structural Engineers Association of New York was mobilizing about 300 engineers to work at the site. And on September 17th and 18th, those 2 days, 400 buildings were inspected with a group of about 60 or 70 engineers. And that was all coordinated by the Sioni group. And then there was a detailed investigation. So this is kind of how the organization chart was. We had New York City Department of Design and Construction. They were in charge. We reported to them. Bovis Lend-Lease, technically our contract went through them because New York City regulation is that they could not award the engineering work to a company without getting at least 3 proposals. Okay. There wasn't a whole lot of time to go out with RFPs and get responses and evaluate. So they figured out Bovis had a existing running contract with the city, and we were able to go through them to work on the job. So that's why Bovis is in there. And so we actually were the lead engineer on the project. We had, now you see all the Sioni groups. What we did is we broke each quadrant. We had a team, and we had a Sioni team in each of the 4 contractor sectors, and then we had our team that went around and just monitored everything. So we had about 35 structural engineering firms that were our sub-consultants on the project. All our competitors, everybody, and it was something that you know, and everybody had nothing to do with competition at that point. And you know, even you know, and there were all these contractors on the job and people running the equipment and everything. And I kind of joke and say, you know, it's the first time that when we would tell a contractor, you can't drive your equipment past that point, they actually listened to us. Okay. So it was an experience. Everybody was totally collaborating, and we all had the same goal. So this is just some photos here of the buildings. You know, in the upper left, I have, you know, the originals, and then you could see what what happened after the collapses and the type of construction. This is buildings 4 and 5. Yeah, this piece right here. This went down about 30 meters into the ground. That was from tower number 2. This came down like a knife. And you could see, actually, I think I took this picture on the right. You can see building 5 in the foreground, building 6 in the back, and that's the piece of tower number 1 facade that was still standing. This is building 7 across the street. This building actually, this is across VC Street, and this actually collapsed that afternoon. What happened was there were fires in that building that started as a result of the collapses, and there was nobody in the building at that point. It had been fully evacuated, and the fire department they had no way to put the fire out. They just let it burn, and it was, I don't know, 4, 5, 6 o'clock that night that building came down. That was the first one that was rebuilt, by the way. Building 7. This was the Bankers Trust Building, 130 Liberty Street, also called the Deutsche Bank Building. This is across Liberty Street, which is on the south. And you can see these pieces of the south tower facade. When they collapsed, they flew over and they went into this building across the street. And it damaged about 9, 10 floors here. This building was very robust. All these lines of columns here in both directions were frames. So it was a very, very redundant type of structure. So the fact that we knocked out one column here for about 9 or 10 floors and some of the slabs really didn't have much effect on the building itself. So we kind of, I mean, it wasn't funny, but we referred to this as local damage on the site, because compared to everything else, this was like very localized. And at one point, they were starting to clean up in that area, and they said, we need to get rid of that piece. And if you look at this, you say, well, you're just going to grab that and, you can pull it out. So we came up with a plan to attach a cable to the bottom, and they can use some equipment, but we didn't want to pull the building down. So we did have the drawings for the building, so we did some analysis, and we figured out you could maybe take up to 50 tons of force before we felt, let's not do any more damage. And we actually connected a cable there, pulled it with 50 tons. Those things didn't budge. They didn't come out, couldn't move them, and they ended up actually just cutting them off in little pieces to get them out. This is Three World Financial Center, which was across the street. We actually designed this building. And the Winter Garden was next to it. And this damage here was in the corner. This is a setback here. You can kind of see it. Well, can't see it from there, but anyway, this is a setback in here. So this whole column in the corner was totally destroyed. And so the only way to support the slabs and everything was to cantilever out some steel beams and hang the slab. We just took some cables and drilled a hole through the slab, wrapped it around, and kind of something you do in your garage, But this wasn't. We couldn't find that connection in any of the steel books that we had, so we were able to make that work. Fortunately, this is where the setback was. Fortunately, there was no damage to this column, because this column carries about 25 stories above it. So that would have been a much bigger problem. And this is, that's what it looked like October 10th, and this is what it looked like on June 27th, 2002. So it was all repaired, the facades, everything. So things were done pretty quickly. The Winter Garden had a lot of damage to it. It actually, this corner of the Winter Garden was held up by all this debris that had fallen down from World Trade Financial Center number 3, what we were just looking at. That all came down, was here, knocked out the column, but it was sitting on this debris. And the fire department was actually controlled all the physical work on the project. The city was in charge, but the fire department, they were deciding where you take out pieces and stuff like that. So they came into our office. We set up a little engineering office on the site. The fire department came in one day. They said, we're gonna remove that debris in 4 days. And we said, well, you can't. We said, well, because there were some firemen that were in that area, including a fire chief, and they said, we're taking that stuff out in 4 days. We said, but it's holding up the Winter Garden. If you take that out, the Winter Garden is going to collapse. So they said, well, you have the drawings, build another one, okay? So what happened was, this was in the AMEC, so now we knew we had 4 days to shore this up. And this was in the AMEC area, and they actually were able, within the 4 days, to get we designed some shoring towers, and they were able to put them in, and they took out the debris. And here's more, actually, that was only in June of 2002 where that facade was done, and it was finished actually by September 11th, 2002. It was pretty much complete. Every morning at about 4 o'clock in the morning, we would have one of our engineers go around the entire site and identify where all the cranes were on the project, okay? And what that capacity was. All these little boxes here, these are cranes. The greens, the blues, they're all cranes, and the circles here is their reach radius. Okay, so and they kept moving every day, so we had somebody go around every morning just to try to keep track of where they were. Now, before we had all these cranes on the job, you know, we had to bring equipment to the project. The contractors had to bring equipment. So our first really big crane challenge was in this area here. This is between building 4 and 5. They had to put a crane in this area to reach over into and this is the slurry wall here, but this is the basement in the pink. They needed to get a crane in there. And, you know, we said, you really can't, there was a floor underneath, so it wasn't on the ground. This was a framed slab, concrete slab, and it really couldn't support what was there. It couldn't support this 300-ton crane. And then one of the engineers realized that there was a big sculpture in that area, and it weighed about, I don't know, 250, 300 tons. They said, if we could get rid of that, then we can, you know, we have enough capacity down below to put the crane. So that's what we did. You can see, well, we had a demolition expert on the project, and he said, I can get rid of that sculpture in, you know, maybe half a day. We'll drill some holes, put some explosive in there, and we'll get rid of it. Well, it didn't work, so they had to chip it away. It took about 3 or 4 days. Okay, so down the left, that's what they ended up doing. And we were able to get the crane on site. And so that was the first one. Then the cranes, there were more and more cranes. There were bigger and bigger cranes. And one day they said, you know, well, I forget which contractor it was. Oh, it must have been Bovis. They said, we need to bring an 800-ton crane, 800-ton capacity on the site. And they had to put it, in order to get the reach to get into the middle, they had to put it right on the edge of the slurry wall. And they couldn't go any further. Now, we couldn't find any beams that were readily available that could support that 800-ton crane. So one of our engineers said, you know, those pieces of the facade of tower number 1 that fell down, those are really big, heavy box columns. Why don't we use those? So we measured them, and here they are here. So we used the existing box columns here, and here's the crane. You can see them to support the crane. So I guess Wolfgang, in a way, this is like recycling steel, but it was a pretty clever idea. Slurry wall was an issue. That's the outline there, and it's 47,000 square meters in area, and it's 21 meters deep, 7 stories. So now, here's the subway lines that go to PATH. These go under the river to New Jersey, and then they all come back. So if you remember when I talked about the top-down construction, where, you know, as you go down floor by floor, you put the slab in, and that keeps the walls from coming in, because this is 21 meters deep. If you have soil on one side, nothing on the other, soil's going to collapse the wall. So in the top down, you go one floor, you put the slab, go another floor, put the slab, and it braces these walls. Now, this wasn't built that way. This was built by digging the trench around there, 21 meters deep, filling it with the bentonite clay, okay, pouring the wall, and as they excavated, okay, so the concrete wall is here, it's 1 meter thick. As they excavated, they would put tiebacks in. So they'd have these long cable anchors, and they drill them through here, and they'd go, there was nothing else here at the time. So they would put them down at angles, like like probably in this tent, they probably have something like guy wires, okay? Only these are drilled into the soil at like 45-degree angle, whatever, and they go into rock. So they put these anchors, they go down one floor, put these anchors in to kind of hold it back, okay? Then they go another floor, excavate, put some more anchors in. So they had several levels of these anchors to really pull back on these walls so they wouldn't collapse. Now the idea was that when they went back in there, and it was a whole, people call it a bathtub, okay? When it was all clear, this was all 21 meters deep, completely open, and it had all these anchors back here keeping the walls from coming in. Then they put the slabs in place, okay? All 7 stories. Now once the slabs are in place, they keep the wall from coming in because it's you know, it's a concrete slab. And you don't need the tiebacks anymore. Now, they didn't cut the tiebacks. There was no reason to cut them. But they were also not protected from corrosion because they were considered only temporary. Tiebacks were only there temporarily until the slabs were put in. And then the slabs were going to brace the wall. So the concern was when the buildings came down, this was on actually Liberty Street. If you look here, this is Liberty. The next picture is a picture taken this way, looking at this slurry wall. And when the buildings came down, they destroyed a lot of these slabs in here. So the concern was if the slabs aren't there and the tiebacks we weren't sure because that some of them might have corroded, is the slurry wall gonna collapse? And if the slurry wall collapses, the Hudson River comes into the bathtub and it goes into New Jersey and then back to New York through the subway system. So it was a big concern, but it didn't happen. So somehow all this debris was holding up the slurry wall. So we said, you can't remove this because otherwise the slurry wall will come down. So that was a concern. This is just a picture showing the subways, New Jersey, all that. So we had a little alarming incident. This is looking in the same direction along Liberty Street. On October 7th, we had a big crack develop on Liberty Street, and the slurry wall is right here. That's where all the slabs were destroyed. Obviously, the wall was starting to move into the excavation. So, you know what to do. You couldn't go in there with equipment because they had all that debris. So the only thing to do was to fill. Now we were trying to remove stuff from the basement. The only solution was to actually put more stuff in there to keep it stabilized so it wouldn't move anymore. So we fill it with sand, but it was more than sand. We filled it with 30,000 cubic meters of material behind that wall that eventually had to come out, but it was necessary to keep the wall from moving any further until we could put the new tiebacks in. So the idea was fill it with sand, dewater, and then install new tiebacks, which were going to be protected from corrosion. And that's what was done. Fortunately, the wall stabilized eventually. I think it moved about 18 inches altogether in, but it didn't fall down. We never had the water problem. So what happened then is, and actually this is Liberty Street here. So these anchors were put in, you can see them, and they're tied back. There were about 1,000 of these anchors put in to hold the wall back so the excavation could be completed. 24/7 operation. It worked around the clock from September 11th through July 1st. And you can see here, this is 3 days before Christmas. We worked through Christmas, New Year's, Thanksgiving, all the holidays. As I said before, we have 35 nationalities in our company, so it didn't, you know, a lot of people don't celebrate Thanksgiving and stuff like that, New Year's. That's the operation. This is the way it looked just about at the end of what was declared the cleanup. Was declared to be finished around July 1st, so this is 3 days before. This is actually interesting here. You're on Liberty Street here. This is the North Street. This was building 7 that came down. So we're looking north now. These were the original slabs. You can see all these slabs in place. Those we decided to keep in to brace the wall because it was very difficult to get in there with any tiebacks, new tiebacks. So those slabs stayed there. at least temporarily, until we were able to do the new construction. This is a couple of more pictures on the left here. That's what it looked like 10 years later. Hard to believe, 10 years later. And that's what it looks like as of this past May. That's the Freedom Tower going up, the new Freedom Tower, topped out now. So that's kind of where it is. So what were the results? The safety, there was not a single significant injury on the project throughout the whole operation, which is quite amazing. I think somebody fell down and broke a rib or something. That was about it. So from a safety standpoint, in fact, OSHA, Occupational Safety and Health Association, they have statistics on construction safety and how many injuries, per on a particular site and frequency. And actually, this had half of the number of incidents of safety problems as a normal project. The schedule, the original schedule was, we sat around after a couple of weeks and we said, contractor said, this is a 2-year project. It's going to be 2 years and cost about $1.5 billion to clean this up. And it actually took 9.5 months and under $1 billion to do. So it was beat the schedule and it was under budget. So you'd like to hear those things, I guess. Okay, I'm gonna try to go a little quickly through these. I know we're running a little late. I think there were some Yankee fans in the audience. I got that impression. This was one of our favorite projects, actually. The old one, it was actually built in the parking lot. The old one is the one on the left, the small one. And that was actually built in 1923, and it was renovated in 1974. But the problem was all the new baseball stadiums these days, it has to have the suites and the clubs and everything else to attract people to spend money and buy these things. So these are some of the statistics. You see 56 suites in the building, 14 lounges, and here I think I got the numbers right. Design was 18 months. This was asked before. Construction 32 months. It was done very quickly. I'm not going to go too much into these foundations here. One of the reasons I went quickly is the use of Tekla, which is a building information management software. And so we're able to model everything. We actually detailed the connections on this, so it saved a lot of time. Here you see the model on the left, the actual construction on the right. This is the Great Hall, if you've been to Yankee Stadium. On the left, obviously, during construction, and on the right, this was done, in fact, that's me with the white hat there. This was a week before the opening, so it was that's why all those banners are up now. And actually, if you look on this side, as the people who are there, you'd know, these are black and white, and I think these are the older players. And then the other way, they're in color, as the newer ones. But it's an amazing space. These are the upper deck columns, and the reason I showed these is the Yankees they didn't want straight columns, okay? They wanted a Y for the Yankees, okay? So we have Y columns. So nothing's easy, they just try to make it difficult. This is the scoreboard, 21 meters by 152 meters. Now, one of the pretty exciting things here was the frieze up above, okay? This is like a Yankee logo, almost. And the original one, on the left is the original stadium, and on the right is the new one, and the original frieze was copper, and it was just connected, it was not structural, it was connected to a supporting structure. The new one is actually, we had suggested, why don't we just make it a structural element out of steel tubes, and you just have one piece, and we did that. And you could see, again, well, the left is the drawing, middle is the computer model, and on the right is the actual construction. And all the connections were made on the back side here, you can see. So all those bolts, so they don't show from the field when you look at it. And it's all structural steel, it's structural supports, the lights and the catwalk all around, so it's actually a structural element. It also, we have cantilevered beams coming out, and it stabilizes those at the end. So it really has it's a real structural function. And that's on the right, the old and the new. Oh, some of the shots here, the concourse level, this is what it looks like on the inside, and the red on the bottom is that level, concourse level, and then we have the reserved concourse, and then we have the upper concourse, and then the suites. You can see on the left all these boxes here. These are all the suites, all around. And some of them are pretty luxurious. So it's, and if you've been there, they have some really nice restaurants and everything. It's quite a structure. So I'm going to finish off here, and I'm going to do these pretty quick. Sorry, we're running a little late. Kingdom Tower, this is the building that we're designing now in Jeddah. It will be the tallest building when it's done. This is a concrete building, okay? We were talking about that before. Totally concrete. That's the location, Saudi Arabia. It's on the Red Sea. That's the current building height. Interestingly enough, the spire is about a third of the height of the building. 337 meters is the spire. And you know, I talked about vortex shedding before, but the building actually, because of the shape, you'll see it's a tripod shape, but the faces are, and you can see it better actually from these posters. The faces are concave, and you can see it's not totally symmetrical like some of these things end at different levels. And by doing that, the shape and the geometry actually reduce significantly the vortex shedding on the building. And it's very, very efficient. Doesn't even need a two-mass damper, although we're making provision for it, just in case. You know, the numbers don't tell you everything. But very slender tower. This is the foundation, the piles. The question came up about piles before. This is how deep they go on this particular building, up to 105 meters, okay, in some cases. And it's essentially a bearing wall, concrete, okay? We have those end walls, which are shown there, okay? And you know, a lot of people will realize that this is the shape of the building, and the more you can put in here as far as restraining the overturning, the better it is. And I think this is a superb example of the architecture and the structural engineering totally coordinated. I mean, it's almost like a perfect structure when you look at it. You have these end walls, and then you have the corridor walls, okay? And you have fin walls, and you have the triangular core. And these all work together to resist the lateral load. Those, the core, let me just to get a sense of the scale. It's, well, not that important. I think it's 37 meters on a side. Anyway, if you notice that little terrace out on the top, it's got a little interesting story here. See that little thing on top? Okay, it looks like a soap dish or something. It's called the Sky Terrace, and originally the owner wanted to make that a helicopter pad, a helicopter's landing. And that's about 600 meters up, 25 meters in diameter. And then they talked to some helicopter pilots, and they said that's not a good idea to do that. So, but the owners liked it, so they, well, let's keep it. So that it's actually going to be like an observation tower up there. So, anyway, the analysis, we were talking to somebody during the break about, you know, what analysis software to use. Well, on this kind of a building, we use 3 different independent types of analysis software. Okay, you know, you got to get this right. So, wind tunnel testing. We did 1, 2, 3, 4, 5 wind tunnel tests, and then we had it with RWDI, who I mentioned earlier, and then we had another wind tunnel testing laboratory do another wind tunnel test just to check it. Okay, and these are all different types of tests. Seismic, we did a time history analysis, nonlinear. Okay, it's not that critical, but the thing I want to point out here is that this shows the lateral load, the shear in the moment due to wind and seismic, and the green line is seismic, and the red line and the blue line is wind. And it's very typical for tall buildings. When you have a very tall building, even though this is a concrete building, and usually, you know, concrete has a lot of mass, which is something you not really like to have when you move in the ground. You don't like the mass. But it's so tall, and it's very typical for these very tall buildings, that the wind actually is more critical than the seismic. It's very interesting, even for a concrete building like this. Right now, the numbers look good. Everything is done. All the wind tunnel tests looks like the acceleration is not a problem. But just in case, in the spire, so maybe this will use up, I know Wolfgang has a problem with this, you know, what are we using this spire for? You know, how efficient is that? Well, we're thinking to put a damper in the spire, so we need that, we really need that, just in case we have to put a damper, and that would be a pendulum type damper. Last slide, the concept design was finished. You saw from the wind tunnel, this was back two and a half years ago. We finished the schematic design in August of 2010, and we had it peer reviewed by another structural engineer, one of our competitors, but good guys, Magnus and Clementic Associates. Again, you don't want to get this wrong, this job. The piling tender went out the end of last year, and the design development was completed in February. This, I believe, they started driving test piles on the project, and as I said before, this one looks like it'll actually get built. Oh, and we also had a internal QA/QC. 2 of our principals, Dennis Poon, Len Joseph, have a lot of experience in high-rise buildings. Len worked on the Petronas Towers, Taipei, etc. Dennis, a whole bunch of other things. He's in charge of the Ping An Tower now, which is another going to be a tall building. Shanghai Tower. So we had these 2 people in our office. Dennis is in New York. Len is in California. Independently review everything. The job is actually being designed out of our Chicago office. So we have New York, LA, checking them. This was the last one. Just some statistics. There's enough concrete to form a sidewalk from Chicago to Miami. That's 2,000 kilometers, okay? Total rebar height, 6 Eiffel Towers, rebar weight, 6 Eiffel Towers. Concrete used would fill 15 Olympic-sized swimming pools, and enough steel reinforcement with a 13-millimeter diameter bar to wrap around the earth 1¼ times. So, pretty big job. Oh, sorry, again, I keep forgetting, I should have looked at this. This is almost the last slide. Somewhere on there, one of the things I do, I actually retired from the firm. I'm still a consultant. I still represent the company on a lot of different things. One of my part-time jobs is editor-in-chief of Structural Engineer magazine. And it's going to be, we're going to give handouts or have them access to a PDF or something, so this information will be there. But I talked to the magazine people. Like I said, I'm only a part-time chief editor, but they agreed to give some discounts here. If anybody's interested in doing it, I hate to make it sound like I'm here pushing a magazine, okay, but they're able to give this special offer if you're interested in doing it. There's a website. If you go on one of these two websites, if it's regular attendee, VIP, there's different deals there if you're interested. I have a copy of the magazine somewhere if you want to show it. And that, for sure, is the end. So thank you very much. We appreciate it.